section 8.5, we build on the concepts from 8.4 to detect objects. In this section, we're going to combine PCL with an action server and client. We'll find a desired object based on context and plane computation. In this section, our code will look for a desired object and use specific context like information about the shape based on a cat model or a gazebo model, and also based on plane computations. Overall, the code works like this. Number one, we instantiate the action server. This class also contains a PCL object and a TF transform. We get the point cloud, and then we're going to compute a coordinate transform with respect to the world. This will facilitate the computation of planes given that the z-values will be similar to one another. Find the table and the table plane first, and then build from that to find the toy object plane, and then return an approximation of the pose of that frame on the toy. So we set up by first starting gazebo with a starting pen, the table, and the toy block. The objects come from the models found in PCD images. So we can start this world with this command. ROS launch worlds table with block. There it is. We will also open our Kinect simulation, but also we'll open our viz pointing at the correct point cloud. We do this with simple camera model, and in this case Kinect simulation 2.launch. So we have the world as the fixed frame. We are looking at Kinect depth points, and currently we just have selected points as an additional point cloud. So this is our setup. And so the action server client will use the context-specific routine to find the desired object. We'll look for the tabletop surface, return the height of the table, and then look for the toy object, starting from the table surface and finding the toy's top layer, where after doing that we compute a plane and then return the pose from the center of the object based on the knowledge of its dimensions. So to start that code, we will run the action server. We're going to use a package object finder. So from here we see instantiating the object finder, action server, subscribers, publishers, going to the constructor of the object finder, listening for the transformation from the Kinect to the base. We find it, and then we get this frame ID set to the base link, the child ID to the Kinect frame, and then we have a vector from the reference frame to the child frame in this direction, and then we have this orientation coming here, and coming here. we can convert that into a quaternion or represent it as a affine rotation or a rotation matrix like this. If we go back to RViz, we also see, let's see, we want to put a marker on the toy object looking at the topic triad display. We still don't have that since we have not started the node. Here we need to run the triad display node to show that marker, and also we need to run the client that's going to specify the object type that we're looking for. At the end, we're going to get this estimated pose for the toy block, which is close to the ground truth. So let's try to run that. So right here, I'll open two more windows. We use the RViz marker package to run the triad display. Okay, and we need to also do the object finder, example object finder action client. So it was waiting for the server. It connected. It sent the goal for the toy object. The connection succeeded. The object was found, and then the pose or the position is returned here, as well as the quaternion. And we were able to find the surface, the table height, and the surface height. We send the goal to find the toy block, the goal of the table, and then we found the toy here again. This is for the table, this is for the toy, and we get these coordinates that are close to the real thing. So I think now we can display that right here and the triad marker. So notice that, sorry, let me zoom out. The marker is centered at, it's placed at the center of the toy, not on the top surface. But we are interested in finding the top surface before we can estimate the center of this object. So you can see just by running the code in this way and using some context information, we're able to get the pose of this particular object. So let's take a look at how that works. So all of our code is coming from the object finder package, and the server code is object finder action server.cpp. So here I might open a new window, and we're working with the server right here. And this is the code that we're going to handle. We'll define the class right here, as we will point out in our presentation. So first things first is the instantiation of the object finder class in main. And within the constructor, we instantiate the action server object. So let's maximize this. This is the definition of our class. Here's our simple action server, goal, result, and feedback. Two more classes from PCL utils and TF listener, finding the table, finding the toy. A callback as a public function, and then after the class terminates, we have the constructor where we instantiate the object finder action server. We're using this action server topic, and we are setting the callback within the class in this way. The action server is started, and we also assign a transform listener. So here in main is where we instantiate the object, call the constructor, and get things running. We also have this transform listener. We're going to be interested in finding the transformation from connect to base, and we will do the lookup transform right here. So let's take a look over here. As we get this transformation between base link and connect PC frame, this of course assumes we have done extrinsic calibration properly, because in fact that's what the extrinsic calibration transformation is, the base link to the connect frame. So we just retrieve that. This is a stamp transform, then we convert that to a regular TF transform. So here what we're doing is we take the object finder class and then access the transform utilities class, call get transform from stamped, so that returns this TF transform that we're calling TF connect with respect to base, and then we wish to convert that TF transformation to an eigentype. So we are going to call that global affine connect with respect to base variable, and we're going to call transform TF to affine 3. By having the transformation from the connect with respect to the base, or from base to connect, we will be able to compute the plane for the table or the toy and have z coordinates with similar values, which makes things easier to analyze. In our callback, that's where we're gonna actually get the point cloud by calling this method we've used before, and then we're gonna transform the connect cloud by using this transformation that we got here. So we get a new coordinate system. We expect the z values to be the same. We're going to start looking for the table, and we're going to use a filter that only looks in a particular range of points, from an x min to an x max, y min to y max, z min to z max, with a particular thickness dz. So we're looking for point clouds here, or a number of points within this filter. And what we're assuming here is that the layer with the most points is going to be the height of the table. So here's our range from 0 to a meter, from negative 0.5 to 0.5 in the y direction, and from 0.6 to 1.2. So you can see that these numbers right now assume some context based on the height of the table and the location of the table, and then we're moving up every 5 millimeters. Once we find the table height, we're going to use the same technique to find the top layer for the toy. So this is the surface height of the table, and then it'll return the object pose. If we know the table height and we know the toy height, we can get the toy centroid, and then that's how we approximate the coordinate frame position. I went quickly through the details of our implementation here for the sake of time, but please take a look at the code and make sense of how we can get this pose for our object. This is a good place perhaps to explore using debug mode and then stepping in through all of these functions right here. All right, see you in the next section. Thank you.